quite possible that when these different ideas are taken together in tandem and are harnessed in conjunction, then you may get surprisingly effective results. And I will try to prove this thesis in today's presentation by using this analogy of robust processing of database queries. So in order to give you an intuitive feel before I go on to the actual database aspects of this presentation, I wanted to give you a real life analogy of the kind of thesis that I have. And so I'll take you back to the Commonwealth Games. I hope you're able to see slide 2, which is Commonwealth Games. This, as you would recall, was held in 2010 in Delhi. And at that time, there was a lot of discussion about the expenses of this particular event. And I'm sure you would have seen all the media discussions about to what extent there was a scam and things like this, right? So at that time, if you ask the estimate of the overall expense of the Commonwealth Games, the government valuation was around 5,000 crores. And you would obviously realize that this is a gross underestimate, because it doesn't even take care of the first level of handouts that have to be given to the various contractors and so on. So obviously 5,000 is a ridiculous underestimate. On the other hand, if you had gone to the popular press, and especially as you know, today we have a hyperventilating media, the numbers that they were quoting at that time was around 70,000 crores. In 2010, 70,000 looked like an unimaginable number, although in light of subsequent events like 2G and other such cases, this actually looked to be fairly conservative later on. But at least in 2010, 70,000 looked like an outlandish number, which was a ridiculously high overestimate and so on. So what you might be tempted to do at this particular point is to say that both the government value as well as the number being, which is being pushed around in the media, these are both ridiculous numbers which have no connection to reality, and therefore we should just discard both of them. But what my point here is that if you take the geometric mean of these two numbers, that is of 5,000 crores and of 70,000 crores, then the number that you get is around 18,700 crores, which, believe it or not, is very close to the actual number that came out from the audit of the Comptroller and Auditor General, which was presented in Parliament, which was around 18,500 crores. So the point here is that by taking two stupid numbers, but by combining them in some intelligent way, you can actually come up with very good estimates of the real value. And this is the focus also of the subsequent talk. Okay, so coming to database systems, since I was told that there was a heterogeneous audience here, I thought I'll just give you the world's quickest introduction into this fascinating field. So database management systems, or DBMS as they are more affectionately known, are these extremely large and complex software systems which run to millions of lines of code. And they are essentially responsible for doing the heavy lifting and the data processing for enterprise level data. So they are expected to handle data through its entire life cycle of data capture, data storage, subsequently querying the data, maintenance, and so on, and providing efficient and convenient mechanisms for processing enterprise data in its entire extent. So not surprisingly, what you would find is that database systems have essentially become the cornerstone of the computer industry, whether you look at it from the computing angle in terms of infrastructure, or whether you look at it with regard to the human involvement. More than 70% of computer professionals in the world are employed in some facet or other of database activity. Or if you, from the financial aspect as well, this is the largest monetary sector of the computer business. In fact, as you might probably know, most of the companies in the world in the entire computing industry as a whole are being supported by the database industry. So even a company like Sun Microsystems, which was one of the most famous developers of new computer architectures, was a few years back bought by the Oracle database company, and now they have dedicated processors that are meant for database applications. Okay, so in the next slide, it gives you a list of some of the well-known commercial and public domain database systems, and many of you may have actually used some of these systems in your day-to-day activities. So on the commercial front, you have DB2 from IBM, then there's SQL Server from Microsoft. HP has a massively parallel SQL MX platform where they provide you the hardware as well. Then Exadata from Oracle is very popular, especially in India. And then there is ERP solutions like SAP HANA and Sybase IQ and so on. And then in the public domain, you have PostgreSQL, which is extremely popular. Lots of people have used the innards of PostgreSQL to develop various kinds of applications. There's also
hello.
Is extremely popular.
Yes. Sorry to interrupt you. We are not able to see your presentation.
Not able to see it, is it? Okay.
Presentation will not. May request all the participants to your webcam off.
Is it visible now?
Presentation is not visible, sir.
Okay, maybe I'll switch it off and start it again. Just give me a minute.
Okay.
It says later. Yeah, is it on the screen now?
Yes, sir. Yes, sir. It is.
Okay. So I just finished the second slide and then moved on to this slide number 4, which is on the background about database systems. Is that visible now?
Yes, sir. It is visible, sir.
Right. So, and the basic point was that database systems are essentially ubiquitous in our day-to-day life, and they're used in all kinds of applications. And there are several products that are available both in the commercial world as well as in the public domain space. Okay, so the reason that database systems are so ubiquitously popular is that they come armed with a large number of goodies. But in particular, I'll focus on 2 of them which are relevant to the rest of the talk. The first is that database systems are the real reason that you can have peace of mind. That is, because any changes to the database underlying contents, they are guaranteed to be immune to any subsequent system failures. So there is this notion of asset properties of databases, where they give you atomicity, consistency, isolation, and durability. And thanks to these properties, what you find is that even though subsequently there might be various kinds of failures at any part of the entire data processing pipeline, these changes that you have made to the database are guaranteed to be immune to them because there are sophisticated recovery mechanisms that are in place to ensure that you get back your original data. So on a lighter wing, I usually like to say that the database system is equivalent to the Sri Sri Ravi Shankar of the information world, minus the long hair, of course, because database systems are much more conservative. The second reason that database systems are so popular is that they provide what is called as declarative access. That is, you only need to state what you want without specifying the mechanism to achieve it. So this is very different from the normal programming that one is used to. So if you do a C or C++ or Java program, and let's say you want to invert a matrix, what you do is that you write a program where every step of the way has to be specified, and you not only say what you want to do, but you also give in complete detail the algorithm to do the operations that achieve this objective. Databases are much nicer. All that you have to do is to say, this is my target goal, and you go figure out how to achieve this goal. Okay? So it's very similar to the way that at least in IISc professors deal with PhD students. That is, we just say, go and write a great thesis and don't ask me how to do it. Of course, I'm sure in Hyderabad, people are much nicer in Osmania and JNTU and so on. They actually write their thesis for the students. But I think in IISc, things are a little more distant, and we often tell the students to go and figure out things on their own. Okay? So this is the one of the key features of database systems that are not shared by any other kind of computing paradigm, where it's only the objectives that are given and the mechanisms to achieve these objectives are left to the system to handle. Okay? So this is particularly true of a special flavor of database systems called as relational database systems, or RDBMS. These are pretty much used in every database system that you have in the world today in one form or the other. And the reason that they became popular is that they are based on this mathematical notion of first order logic augmented with existential and universal quantifiers. So there's a very strong mathematical foundation. And this was designed by Ted Cord of IBM Research. And for this, he received the Turing Award in 1981. And since you're all ACM members, you would know that the Turing Award is equivalent to the Nobel Prize in Computer Science. And it has also led to the saying in the database community that we believe in God and not God. So the basic idea here is that all data is stored in a set of relations. And for the purpose of this talk, you can think of a relation as the mathematical equivalent of the normal table that we are used to, where there are rows and columns. Okay? So all that we have is that all the information is being stored in a two-dimensional setup where there are columns which are the schematic information and there are rows which hold the instance information. So essentially these tables have attributes, relationships, and constraints. So to give you an example, here is a simple university database where there are three tables. There's a student table, there's a course table, and there's a register table. So in the student table, the schematic information is the roll number of the student, the name, and the address. Similarly, in course, you have the course number, the title of the course, and how many credits you get if you successfully complete the course. And then the register table combines the information in these two, in the student and the course tables, by telling you which student through the roll number and which course is taking which course through the course number, and the specific grade that was obtained by the student in this particular course. So this is the schematic information, and here are some of the rows that you could have in each of these tables. And so I have said that Jayanth, who is a student from Bangalore, has taken the database course which is called as E0261 in IISc. And since I made up this slide, I was very kind to myself. I gave myself an A+ grade in this course. So this is what a very simple but extremely powerful concept, that all information is stored essentially in tables or in their mathematical equivalent, which is the notion of a relation. So now if you wanted to ask questions on a database that had information stored in a relational database, there is an intergalactic standard called a structured query language, or SQL. This was again invented by the IBM's Almaden Research Center, along with most of the great database ideas all came from this particular center. This was in the 1970s. So here, if you want to ask the question saying, please list the names of students and their courses, what you would do is to write what is shown in the center box there. So ignore the keywords which are shown in green, which is select from where. What this is basically saying is, please pull out the names of the students and the titles of their courses. Where should I seek this information from? This information should be taken from the student table, the course table, and the register table. And how do I make sense of the information across these different tables? That is by ensuring that there is a matching between the roll number of the student from the student table and the roll number in the register table. Similarly, that there is a match between the course number in the register table and the course number in the course table. So this is the way that one would specify this specific query, which would, for example, could well be asked by a department chair or by a vice chancellor saying, just give me the names of all the students and the courses they're currently taking. So the important point to notice here is that SQL is a declarative language. That is, it only specifies the target goals and not the means. So what has been left unspecified in this particular query that has been issued to the database system is that this notion of matching the predicates, that is the student roll number with the register roll number, and similarly the register course number with the course number, is called as the join operation in the database lingo. That is, you're joining the information in two tables. So what has been left unspecified is the join order. So if you use S, R, and C to represent the student, course, and register relations, you could have done a join of S with R first. So the join is usually shown with the bow tie symbol that you see in the center of the slide. So let me just highlight that. Let me see this. I was trying to get the pointer to work here. Yeah, so you can see this here. This is the bow tie symbol, which is the mathematical symbol for join. So you could have chosen to first join the student table with register using roll number as the matching column. And then you could have chosen to do the subsequent join with the course table, which is the second join here, where you're matching the register table's course number with the course number from the course table. Or alternatively, maybe for Vastu reasons, you could have chosen to do the join of the register table with course first, and then do the join and then subsequently do the join with the student table here. The reason that both of these two alternate sequences would have produced the same answer is that the join can be easily shown to be both a commutative as well as an associative operator. See, the output of both these alternative sequences or orders would have been exactly the same. There would have been no change in the answers. But there is a huge difference with regard to the running time of these two different sequences. The first sequence may run in a few seconds, whereas the second one may take years to complete. Okay? So that is the kind of differences that we could potentially have by choosing different orders. So it's primarily a performance issue. There's no difference in the correctness, but the performance could be very different depending on which sequence you chose. Now, even if you had decided the sequence to be, let's say, the first sequence which we show here, which is the student join with register first and then subsequently join with the course, what has been left unspecified is that the join is a logical operator saying, let's combine the information in these two tables and make sure that there's an equality on the roll number. But with regard to the physical implementation of the join operator, there are many different options available. Over the course of the last 4 decades, many different algorithms have been designed and implemented. So there are algorithms called as nested loops algorithm, which is essentially nested pointers going through multiple tables. Or you could use the sort merge algorithm, or there's a hash join, there's an index join algorithm, there's a semi-join algorithm, and so on. So there is a large number of different implementations available for this logical notion of a join operator. So 2 things have been left unspecified in the query: the sequence of joins as well as the implementations for each of these logical join operators. Now, who's going to figure this out? This is left to a component which is within the heart of the database engine, which is called as the query optimizer. So you don't see this when you're interacting with the database engine, but it's just below the surface. And this query optimizer component identifies the optimal evaluation strategy. That is, what is the best way to achieve the objectives that you have given. And typically this is known as the query execution plan. That is, the strategy is known as a plan. And we will use the word plan during the remainder of this talk to represent this strategy. So in this next slide, which is slide number 11, I am showing you a sample execution plan. This is a physical implementation of the logical objectives that you have. So corresponding to the query that you saw in the previous slide, where you wanted this information about students' names and their course titles, this is the physical implementation of how you would achieve that particular result. So what you see here is that in each of the ovals that you see, there is a specific database operator. So the plan is always a tree of operators which have to be evaluated in a bottom-up fashion. At the bottom, you see all the tables that we had originally had from the user, which was the student table, the course table, and register table. And what this particular plan is saying is that first do an index scan on the course table and then join it using a sort merge join with the register table. How would you access the register table? By doing a sequential scan of the table followed by a sorting. And then subsequently, there's a hash join which is done with the student table, which has been accessed through a sequential scan, and then out comes the answers. The specific operators and the techniques are not very important for the purpose of this talk, but I thought let me just show you an example of what a database plan looks like. So this tree of operators is what is going to be actually implemented within the database engine to achieve the goal of the original query, which was to produce the names of the students and their courses. Now you would also see that each of these ovals, which are the operators, are annotated with 2 numbers. The 2 numbers, there's a green number and a red number. The green number tells you what is the number of rows that will come as the output of this particular operator. So for example, if you look at this bottom operator of the student, which is the table scan, there is a number saying card equal to 1000. What it means is that on the output of this operator, 1000 rows are expected to be sent to the next operator downstream in this tree of operators. So similarly, what you would see, for example, in the course table, so I've put the pointer here, you will see that the card is 100, which means that it's expected that 100 courses will be propagated to the next operator downstream, which is the merge join operator. So essentially, it's telling you the volume of traffic from one operator to the next within this tree of tree structured plan. The other number that you see, which is cost, which you, for example, in the student table, you see that the cost is around 7,000 or so. This tells you how much effort is involved in producing this output. So we know that the expected output is around 1,000 rows, and the cost tells you how much effort is involved in producing this output. So in every operator, you'll have two numbers. One is the cost of execution of the operator, and the other is what is the volume of output that is produced by it. Okay? So you can think of it as equivalent to a water network, where the cost is equivalent to the cost of opening the valve, and the cardinality tells you how much volume of water is going from one valve to the next in this pipeline network that you have for water distribution. Okay, so now let's figure out how does the database system automatically decide what is the best possible way to implement the declarative query that you gave, where you gave only the objectives without specifying the mechanism. So the way that it works is that you give your SQL query, which is what you see here as the input, and then it comes to this query optimizer. The query optimizer is actually a fairly complicated component of the database engine. It uses a dynamic programming based exercise to come out with the optimal plan on the output side. Now, optimality can be defined in many different ways. It could be based on the amount of resources, or it could be latency and so on. What we will assume for the purpose of this talk is that optimality is defined in terms of response time. That is, you want the fastest way to execute this query and achieve the objectives that you had specified. So in order to do this, there are two models that are input to the database query optimizer. One is called and these two models refer to the green and red numbers that you saw in the previous slide. So the execution cost model is an estimate which tells you how much effort you think it is going to take to produce the output for this particular operator. And this is essentially a function of the kind of hardware that you have. That is it a CPU alone machine, or is it a general purpose machine, or does it have accelerators, does it have GPUs, and so on. And it's also a function of the database engine software in terms of how well the software was written, what are the kind of resources that it's using, what is the kind of algorithms that have been implemented, and so on. On the right-hand side, you see the other model, which is the cardinality estimation model, which tells you what is the expected output of each of the operators. Now, this one is a function not of the hardware, but it's a function of the data. It's a function of the distributions of the data within each of the columns of the tables in the database, and it's a function of the correlations across different columns of either the same table or across tables in the database. So the left-hand estimation model, which is the cost model, that's primarily based on the hardware and software platform that you have. The right-hand side cardinality estimation model is a function of the actual data that you have in your database. So using these two models, the query optimizer is supposed to come up with the ideal solution. And as I said, ideal means the fastest algorithm to achieve the objectives that you specified in your declarative query. Okay, so now the problem is that this supposedly optimal plan choice that you have made, which is at compile time, when you submitted the query, the database system said, oh, I think this is the best plan. At runtime, it may actually turn out to be highly suboptimal. And when I say highly suboptimal, I don't mean by it's slower by 20% or 30%. In fact, it will be spectacularly worse. It could be often 1,000 times worse. That is, the query will run 1,000 times slower than the intended speed when the query is executed with the specific plan that was supposedly the optimal choice. Now, why is it that we are making such terrible mistakes? The reason is that the adverse effect is due to errors in these two input models. We had two estimation models. One was the red number, which is the cost model, and the other was the cardinality model. So the errors in the cost model usually have only a limited impact because it's reasonable to assume that you can come up with a fairly good characterization of both the hardware and software. So usually it causes only about 30 to 40% error. But the cardinality model, on the other hand, often has a huge impact. And I'll show you some examples of this as we go along. There are a variety of technical reasons as to why the cardinality model produces large errors. And some of them are listed here, like core statistics, attribute value independence, multiplicative error propagation, query construction, and so on. So I don't want to go into the details of all of this. There is a huge body of database literature on this, but just take it from me for now that often the cardinality model makes huge estimation errors. Okay? So in case you don't trust me, here is a proof by authority. And what you see here is the picture of the handsome Dr. Guy Lohman, who was essentially the father of the IBM's DB2 product with regard to the entire query processing, optimization, and execution component. So a few years back, this is in April, about 6 years ago, in April 2014, he put up a blog post, and the title of the blog was that, "Is query optimization a solved problem?" with solved being in quotes. And what he complained about there is that although he had been working on this problem for the last 3 decades, he says that really we have not made much progress. And then he goes on to write in extremely colorful language, as you will see on the slide. He says that the root of all evil, the Achilles heel of query optimization, is the estimation of the sizes of the intermediate results that go from one operator to the next, which are the cardinalities. And he says that these output cardinality models can easily introduce errors, not of a few percent, but of many orders of magnitude. So we usually make errors in the thousands, in the 10,000s, in the millions, and so on. So then he ends with this very cynical comment. Okay? He says, with such errors, the surprise isn't why the optimizer picked a bad plan. Instead, he says that you should be shocked, and very pleasantly shocked at that, as to why would the optimizer ever pick a decent plan. So if you get a decent plan, if you go to Tirupati, you might get a decent plan. Otherwise, you're most likely to have terrible plans. So in general, you will get poor plans. So this is why I like to state it equivalently as worst case is equivalent to average case in database systems. Normally, it's the other way around, that you usually have the best case occurring often, and occasionally you have a bad case. In database systems, it's the other way around. The bad case is the norm. And if you get lucky, then you might occasionally get a decent plan. Okay? So you might be wondering, saying, look, these database folks have been working on all these components for the last 4 to 5 decades. What have they been doing? Have they been sleeping all this time? So just to give you an analogy in the real world as to why although people have worked on it for a long time, it's really a very hard problem. Look at a much simpler problem compared to the database world. Look at the simple election predictions that we are supposed to be doing. And every 5 years, we go in through this exercise. And people are asked in these various kinds of polls, saying that who are you planning to vote for? And all that we have to come up with a binary evaluation of what a party that somebody is voting for, and you need to predict the winner. Okay? But if you look at all these predictions that have been done over the last decade, you see that most of them have come up with spectacularly wrong answers, even for these very simple binary questions. Okay? So just look at the Tamil Nadu Assembly elections in 2011. Both the pre-polls as well as the post-polls all claimed a very close race. And if you look at ORG, for example, they said that it's essentially neck to neck. It's about 120 seats for the DMK party and about 110 for the AIDMK party and so on. But interestingly enough, what you found when the actual results came out is that Jayalalitha had not listened to any of these polls. And in fact, it was a landslide result for the AIDMK party. They completely demolished the DMK. So it was not a close result by any stretch of the imagination. You had 200 plus seats for the AIADMK and only a paltry 30 seats for DMK. Okay? This was even worse in the Delhi Assembly elections of 2015, where there were 70 seats up for grabs. And there you found again that everybody was saying it's neck to neck between the AAP party and the BJP party. And a specific poll like C Voter said BJP is marginally ahead. It's 36 seats versus 31 seats. But then if you actually went and looked at the results, Arvind Kejriwal, being a good IITian, had not listened to any of these polls, and you found that the AAP had completely demolished the BJP party in that particular election. They got 67 seats out of the 70, and only 3 were left. And I actually like to say that they probably gave the 3 seats because they wanted some opposition so that you could have somebody to beat up with in the assembly. Otherwise, it's boring to speak only to your friends. You need somebody else to criticize. So if you look at did you have a problem that the slides have gone away? Because again, I got this, you are no longer presenting.
We are able to see the presentations.
You're able to see, okay, because I got a notification saying I'm not presenting, but okay, just let me know in case slides disappear.
No, it's now, yes, sir. I'm not able to see the presentation. Can you
okay,
please?
let me try to bring this up again first.
You just need to pin the screen.
Yeah. I had done that, but for some reason in the middle, sometimes it seems to be disappearing. Has it come back now?
Yes, sir. I'm able to see.
Yes, sir.
Okay.
Thank you.
Yeah. Okay. Sure. Yeah. Occasionally in the middle, suddenly on its own, it seems to be moving to a paused mode. Okay. Yeah. So if you looked at all these assembly elections that you had, and even a more recent example is the UP elections and so on, all of them were claiming fairly close races, but you actually found that the errors that were made by these poll agencies, both the pre-polls, exit polls, were huge errors. These were completely landslide results and were in no way close numbers. And remember that these are just very simple questions that are being asked. Who are you voting for? And essentially it's a binary in all the elections that I've shown here. Is it X or Y? And even in spite of that, you make enormous mistakes. So in the database world, it's much more complex because you have an entire tree of operators and you have to do a large number of estimations of both costs and cardinalities, which are being propagated through a sequence of operators going down through this tree, which is the plan structure. So people have been working on this for a long time. Okay? And in a sense, you can think of it as three strands or three different styles of approaches have been used to address the problem. The first is to say that let me use better and better mathematics in doing this estimation, because currently most database systems use what are called as histograms, which are coarse piecewise linear approximations of the distributions. So people said that if I use better mathematics, maybe I can do a good job on this. And what you see in this list of things that you see here, Sigmod 99, VLDB 2001, 2009, and so on, these are all some recent papers that have appeared on the estimation problem using the particular approach. And the reason I just listed them out here is to convince you that this is still a very active field of research in the database community. Okay? And the kind of techniques that they suggested is, so one group suggested let's use the wavelet notion, which came from the mathematics community, to come up with wavelet histograms. Others said let's use autonomic computing and come up with self-tuning histograms. And then everybody loves machine learning today, so there are deep learning histograms and so on. So this is one technique that people have chosen to use, where we say that let's come up with better mathematics to address the problem. Another approach has been to say that let me use robust plans instead. That is, although I'm making mistakes in the models, let me use plans that are relatively less impacted by the kinds of errors that are being made by the cost and cardinality models. And again, you will see that there's a whole sequence of papers starting from Sigmod 1994 down all the way to 2010, and there have been subsequent papers as well, which have essentially proposed different kinds of techniques based on this kind of ideology. Okay? I should also mention that in case you're not familiar with the database world, Sigmod, VLDB, PODS, ICD, these are the top international conferences where people present the very best of database research. So as you can see, all the international database researchers have been working on these problems. And then the last technique is what we call as re-optimization. And the idea here is very different. So they say that at compile time, I'm going to make a particular plan. But what I do is that at runtime, I can check the quality of my estimates. So at compile time, I thought that maybe 1,000 rows will go from the student table to the join, subsequent join. And then I'll keep monitoring this at runtime while I'm executing this plan. Now, if I find that there's a big discrepancy between what I thought I will get and what I'm actually getting, then I will go back to the drawing board and do a re-optimization of the query. But when I go back to the drawing board, the difference is that now I know the correct value. So although I thought that there'll be 1,000 rows going from one operator to the next, now I know that it's actually 10,000 rows and that I had made a bad mistake. But now I know the correct value, go back to the drawing board, re-optimize the query using this correct number and come up with a new plan. Okay? So again, even in this strand of work, there have been several papers starting from 1998. As you can see, there have been a sequence of papers. And again, even now, There have been in recent years as well different proposals using this kind of approach to address the query optimization problem in databases. So in case you're not familiar with these kinds of styles of solutions, I thought that I'll give you an analogy. I love sports and movies, so I can give you an analogy in the cricket world. So you can think of these three techniques as being the VVS, Lakshman, Rahul Dravid, and the MS Dhoni techniques. The first is that, since you're all from Hyderabad, of course you love VVS Lakshman, I'm sure of that. So what was Lakshman was renowned for was for the elegance of his play, and especially, for example, things like the late cut. Of course, sometimes he would late cut the ball after it hit the wickets, but just like ML Jaisima, who was his mentor, Lakshman was one of the most beautiful players that we ever see. So that is what you can think of as being very sophisticated mathematics. Whereas the robust plan approach is like the Rahul Dravid approach, saying irrespective of the kind of wicket that you have, I can be assured that he's going to play reasonably well and get some runs on the board, irrespective of what the wicket actually turns out to be. So you can think of the cricket pitch as being the you need to estimate as to how it will behave. And those of you who have been watching the cricket matches will know that people like Jeffrey Boycott or our Sunil Gavaskar, just before the match starts, they go and usually push a key into the pitch, and then they make predictions saying, is this going to be a bouncy wicket, or is this going to be a spinner's paradise, or is it going to be a flat surface, and things like this. So the idea is that in case you make mistakes in these estimations, Rahul Dravid is going to be a good source of runs, because his technique is strong enough that irrespective of the kinds of errors that you made with regard to the estimation about the wicket behavior, he's going to play well. Whereas the re-optimization is more like Mahendra Singh Dhoni, because remember that in all our one-day internationals, what Dhoni was renowned for is that he was the master of being able to adapt to the current situation. So you go in assuming that you are going to have plan A and this is how you're going to play. Often the plan A doesn't work and you find that you have lost quick wickets. Then Dhoni was able to come back and say that let me change the nature of the game, let me go on to plan B, plan C, and so on, and adapt your style of play to the current situation in the cricket pitch. So this was a dynamic re-optimization where you change the plans based on the situation in the game. So in that sense, you can see that the different styles of solution techniques that have been adopted by the database community can fall into these three classes of approaches. Okay? Some of which are compile time approaches, some of which are robust approaches, and the other is the runtime approaches. But just like our cricket team cannot guarantee you perfect results, although even here, although there are several novel ideas and formulations, there are no performance guarantees. Okay? You can try out these various approaches, but you have to cross your fingers and your toes and pray very hard before you are able to get good plans which will effectively solve your query that you had submitted to the database system. Okay, so now this is where we come in. This is, as I said, a very classical problem which has been going on for the last about 3 to 4 decades. And in our lab, we have come up with a completely new query processing technique, which is called as plan bouquets. And what we do is we change the rules of the game. Okay, so if you look at the previous slide, the fundamental assumption was that let us do estimations, and then let us do estimations in better and better ways. What we said is that the only person who can do estimations correctly is Rajnikant. Okay? Because as you know that he's the person who can do the impossible. But for human mortals, it's not possible to do this correctly. Therefore, we completely abandoned this process of doing estimations and said, let us come up with a completely new technique, which is not predicated on this estimation-based models. So in our plan bouquet approach, we do runtime cardinality discovery. So we don't do estimation, but we do discovery instead. And this is done using a compile time selected bouquet of plans. So we use many different plans in the execution, as you'll see later. And therefore, this is a completely new approach to the entire query optimization and execution process. And what is surprising is that with this new approach, for the very first time, you can actually provide performance guarantees. And the performance guarantees is with regard to an omniscient oracle that magically knows all the correct values for both the cardinalities and the costs. So one of the things that I forgot to mention earlier is that it is easy to prove that if you have the ideal cost and cardinality values, then the database query optimizer, which is based on this dynamic programming style enumeration exercise, is actually produces the ideal solution. So compared to the ideal solution, can we come up with performance guarantees? And what I'll actually show you is that if you look at, for example, one-dimensional queries, you can actually give a relative guarantee of 4. That is, we'll be within a factor of 4 of the ideal. And in practice, so this is a worst case performance guarantee. In practice, actually the empirical performance is well within these bounds, even on industrial strength environments. Okay, so now I'll move on to this new notion of plan bouquets. But before I do that, are there any questions about what we are planning to do?
Maybe at the end.
Yeah, okay. So, fine. So I'll now move on to the notion of plan bouquets. So this actually forms the PhD thesis work of Anshuman Dutt, who graduated in 2016. He is now a member of the Microsoft research group in Redmond in the US. And so this was a very influential thesis for which he was primarily responsible. And the basic idea here is that I'll start with the problem framework. So firstly, what we will do is that from this notion of cardinality, which is an absolute number, which tells you the number of rows that are flowing from one row to the next, from one operator to the next in the plant tree, we will instead use this notion of selectivity, which is a normalized version of this cardinality. So it goes from 0 to 100%. And essentially what selectivity does is it's the ratio of the estimated output rows normalized to the maximum number that you might expect here, okay? And then multiplied by 100 to get a percentage. So to give you an example, suppose you had this predicate which said that the fees for the course should be less than, let's say, 1,000 rupees. Now what we are saying is that of all the courses that you have, let's say there were 20,000 courses. So that's the 2 into 10 power 4 that you see here, which is 20,000. Now let's say the output is, the expected output is 4,000. That is, only 4,000 courses are the cheap courses, which are costing less than 1,000 rupees. All the other courses are more than 1,000 rupees. Then the cardinality would be 4,000, but the selectivity would be 4,000 divided by 20,000. So 20,000 was the maximum number of output rows that you could have. 4,000 is the estimated number. So 4,000 over 20,000 is the 20% that you see here. Okay? So it's just a normalized version of the same value. So here, if you look at the query that you see on the right-hand side, this is an SQL query, which says, give me all the information. So star means all the information from the tables, which is student, course, and register. And how are you trying to make sense of this information? You are combining the roll number of the student table with the roll number of the course table. Similarly, the course number from the course table with the course number from register table. And you're restricting this to the cheap courses, the courses which cost less than 1,000 rupees. Okay, so this is the SQL query that you had given. And based on this, you can now come up with a 3-dimensional surface, which is what you see in this slide here. There's a cube below that you see. And in each of the dimensions of this cube is the selectivity of one of these predicates. So for example, you will see that on the x-axis, you have the selectivity of the course table. And what does it mean? It means that what is the selectivity of this predicate of the fees of the course should be less than 1,000 rupees. And that goes from 0 to 100. Similarly, on the y-axis, you have the selectivity of the join predicate, which is the join of the course with register table, which goes from 0 to 100%. And then similarly, you have on the z-axis, you have the selectivity of the student joined with register, which again goes from 0 to 100%. Okay? So this is the 3-dimensional cube that you can draw. And on this surface, or in this volume, what you can do is that you can say that let's assume that the estimated selectivity location in this space is Q sub E, which is what you see on the left-hand side here. And in the cube itself, you'll see that there is a red point. So I'm showing that with the pointer here. And that could be, for example, that you estimate that these 3 different selectivities would be, let's say, 5%, 2%, and 8%. And then there is the actual runtime location that you see when you execute the query. This is the Q sub A that you see on the left-hand side. And in this particular query, for example, it might be that the Q sub A turns out to be 75%, 62%, and 85%. So these are the typical kinds of errors that you see. As I told you earlier, often you make huge mistakes in these cardinality estimations, and there are a variety of technical reasons for these mistakes. It's not that people have been lazy, it's just that it's a very hard problem by definition. Now let's assume that you use P sub OE, which is the optimal plan at the estimated location. So this is the optimal plan which was supposed to be here. Notice that you would be using this at the actual location. Now at the actual location, the ideal plan could have been P sub OA, which is what you see here, which is the optimal plan at the actual location, at the green location. Now, because you are using the red plan at the green location, there could be a sub-optimality because of using the wrong strategy. So the sub-optimality that you see here, given that you estimated it to be at Q sub E and it's actually at Q sub A, is the cost of using the red plan at the green location divided by the, or normalized to the cost of using the ideal plan at this location. So obviously this number is going to be anywhere between 1 and infinity. It's going to be 1 if it so happens that the red plan is also optimal at the green location, or it could be much worse. And there is no way in advance that you can specify what is going to be suboptimality. It could be arbitrarily worse. And that's the reason that we show infinity here. Okay. Now what we could do, so this is for a specific combination of the estimated location, the actual location. Now if you do this over all possible pairs of locations, estimated and actual, you get what is called as the maximum suboptimality, or MSO. Okay? So this is the nightmare situation where you have the worst case behavior, where because of using a particular plan in the wrong location, you are getting a terrible reduction in the, or degradation in the performance. Okay. So now in the subsequent analysis, we will only use a very simple and basic assumption, and this is of what is called as plan cost monotonicity. And what it's essentially saying is that, let's look at the cube on the right hand side that you see here. Let's say the cost of a particular plan at this location is 100. Let's say this is 100 units of time. Then all that's assuming is that the cost of the same plan P within the cube, which starts at the origin and ends at this location Q sub 2, is going to be less than 100. Okay? So that is what is shown in the left hand side. That is the cost of plan at location Q1 is going to be less than the cost of the same plan P at location Q2 if Q1 is spatially dominated by Q2. Okay? So essentially what it's saying is that spatial domination implies cost domination. And in a practical sense, what it's saying is that as you move towards the origin, the amount of data is less, because you remember that the origin corresponded to very low selectivities, which means very low number of rows are coming out from each of the operators. As you move outwards in each of the axes, the number of rows are increasing. So if I give you more work to do, it takes you more time to do it. That's all that this slide is actually saying in a mathematical sense, is that with more data being processed, it takes you more time to do it. Now, surprisingly enough, this need not always be true, although it looks commonsensical to assume that with more input, it's going to take more time to produce it. There are certain operators in the database world like negation and in and so on, which could actually result in less time being taken for more complex queries in terms of the amount of data that's being processed. But we will not look at them for right now. We'll just look at this kind of situation where spatial domination implies cost domination. So let's look at how do contemporary database optimizers behave on for the simplest case where there's only one dimensional. So it's not a cube with 3 dimensions, but it's just a single dimensional space. So here, if you look at it, the ideal situation would be that on the x-axis, what you see is the selectivity of the course table. This is with regard to the fees, that is the cheap courses, which goes all the way from 0.01% to 100%. On the y-axis, what you see here, and I'm showing you again with the pointer, is that it goes all the way from 6,000 to 6 million. And this is the cost of running this particular query for the various selectivities. And the green line that you see is the ideal. So the green line tells you essentially what would be the ideal solution in this entire process. And this green solution is actually composed of many different plans. Okay? So as you go along, for the initial selectivities for, let's say, between 0.01% and up to around, let's say, 0.2%, the ideal plan here would be the plan that you see here, which is called as P1. What you see in yellow there are the tables. That is, C is course, R is register, and then S is student. And the ideal plan would be to combine course and register with the nested loops join, which is what you see here, and then again with the nested loops join. Okay? So again, the details are not important. It's just that a particular plan is ideal in this space. Now, as you go along and cross, let's say around 0.2%, now the ideal plan changes. So here, the ideal plan is that you need to join the course table with the register table using the nested loops algorithm, and then subsequently join it with the student table using a merge join algorithm. So you see that there's a change in the physical implementation that you're using for the join operator. There's also a change in the join sequence. So remember the original slide, I said you have to decide the join order and the join implementation. These are the changes that you see here. Then if you go along and look at plan P3, now you see that the register and course tables are being joined with what is called as a hash join, and subsequently there's a merge join. Then there is a plan P4 where both the joins are hash joins, what you see here and here. And then the last plan is P5, where you see that there is a change in the join order. You are first joining register with student, and then you're joining it with the course table. Okay? So these are different plans being used at different locations in the space. And these are the ideal plans for each of these locations. Now, if you extend each of these different plans, their behavior over the entire space, what you will see is that, as would be expected, P1 is optimal in the initial part of the space, as the red plan. Then the P2 takes over. So P2 is in the initial part. Was there any comment? Okay. So there is then the P2 takes over here. Then P3 is ideal in this space. Then P4 becomes ideal, and then P5 becomes the ideal plan here. So let's look at the possibilities for errors here. So what would happen, for example, is that instead of the green line that you have here, in real database systems, you may actually wind up with the red line here, which is what you see above. And remember that on the y-axis is on a log scale. So the gap between the red and the green is actually very large. So both the selectivity axis on the x-axis on the y and the cost on the y-axis are both in a logarithmic scale. So this is a log-log plot. And what you see is that there's a big difference between red and green. Okay, how could this happen? So green is the ideal case, whereas the red is what you might happen in the real world. So let's look at one extreme. Let's go to the right-hand side extreme. And what has happened here is that the estimated location of the query was just 1%. So you thought that only a few rows will come out as the output of this query. And therefore, you use plan P1 there, because plan P1 is supposed to be very good for low selectivities. But then to your horror, at runtime, what you found, so this is the actual user bay, you found that a large number of rows came out, and it was actually 99%. So you used the plan P1 in the location which was supposed to have been used by P5. And because of this, you had a degradation in performance, and the degradation is as large as 20. So this is 20 times slower because you used the wrong strategy. The similar thing can happen at the other end of the spectrum, where you thought that a large number of rows will come out. So the selectivity was 80%, but it actually turned out that it was only a trickle. So the actual value is only 0.01%. And here the ratio now was going to be 100. So the sub-optimality was 100 here. And if you measure this over the entire space, you find that the worst case behavior was at this left extreme, where the maximum sub-optimality was 100. Okay? So this means that you are 100 times slower than the ideal. Okay, so now let's look at how does the plan bouquet behave in the same world. So what we do is we take this original ideal graph that you saw earlier, which was composed of these 5 different plans, and then we do a very simple exercise. We do the step 1, and step 1 is to draw lines which are horizontal lines across this space with a cost ratio which is r equal to 2. So essentially this is a geometric progression. So let me draw the lines which should make this clear. So here you see the horizontal lines being drawn. They're equidistant because this is on a logarithmic scale. So what you will see is that this first line that you see here corresponds to 12,000. Next line is 24,000. then 48,000 here, 96,000 and so on. Okay, and it goes up all the way till the maximum that you see here. And what you do, so you draw these horizontal lines, which are essentially following a geometric progression, which is a doubling algorithm. So each value is double the previous value. And then you find the plans that occur at the intersection of this optimal profile that you had, which was the original green line, with these horizontal lines that you have drawn. Okay? So you'll see that these are the black dots that you see here. These are the intersections. And you look at all the plans that are present at these intersections. So in this particular case, it's plan P1, P2, P3, and P5. Okay? This forms your plan bouquet. Notice that plan P4, which was optimal in between these two horizontal lines, will not be reflected at all here. Okay, given this initial work, now what we will do is that the execution pattern is very different. Let's assume that the actual value of the selectivity is 5%. We don't know this, but this is where we are headed towards. What the plan bouquet will do is it will not even try to do the estimation. Okay? So what we will start with is we'll assume that the selectivity is low and actually execute plan P1 with the budget assigned with the horizontal cut you had here, which was 12,000. So think of it saying that I give you 12,000 rupees and say, please execute P1. Now, what will happen is that when you give this budget in time, it will not complete. The reason that it will not complete is that remember we had this plan cost monotonicity, which said that in the interior space of any location, the cost is going to be lower than the cost that you're going to have at this location Q2, which means that the cost of executing P1 at this location 5% is going to be definitely more than 12,000. So 12,000 is insufficient to execute this query. I don't know where the actual location is, but given that the actual location will turn out to be 5%, this is insufficient. So then what you do is you jump to the next line, which is here, which is again the plan P1, and now you execute it to double the budget. So now you give 24,000 units of time and say, please try to complete. Again, what will happen is that it will not complete. And notice that if it doesn't complete, we have to throw away the results. So now you go again to execute plan P1, you go here and you keep doing this, okay? And none of them will complete. Then you go to plan P2, which is this other plan which is optimal here. You execute it to this budget, which is 1.9 lakhs of units of time. That will again not complete because it's to the left of Q sub A. So anything which is to the left of Q sub A will not complete in time. Then you go to plan P3 now. And because plan P3 is to the right, so if you look at it, it's a little bit to the right of Q sub A, the budget assigned to it, which is 3.8 lakhs, will actually result in completion. So now, it will actually not require the entire budget of 3.8 lakhs. It will complete with 3.4 lakhs units of time. So it's essentially in 3.4 lakh seconds, this query will complete its execution. Okay. So now look at the overall picture here. And here, this comes back to the original thesis of this talk, which is that there are very stupid ideas here. Why is this a very stupid algorithm at first sight? That is because we are expending lots and lots of wasted effort at the original planning time in order to provide that what we call as the green line, which is technically known as the parametric optimal set of plans and the profile due to that. So it's called the POSP cost profile. That's essentially the green ideal line that you saw earlier. So it takes a lot of time to produce that green line. And then subsequently at execution, we are doing this trial and error mechanism where you try each plan for a certain amount of time. And if it doesn't complete, you throw it away. You throw away all the work you did and start all over again. Okay. So this on the surface seems a recipe for disaster, that you are making terrible mistakes and you are wasting a huge amount of effort in trying to produce the answer for this query. But what is surprising is that because we have these two stupid ideas, they work surprisingly well in tandem, and that I'll quickly show that to you in the rest of the talk. So let's actually look at how much wasted work we did. So that is shown to you in this next slide. So look at the amount of investment we made. We did 12,000 units of time. So this is given in exponential notation here, 0.12 E5, then 24,000, then 48,000, then 96, then 1.92, and then 3.4. If you add up all these investments, that's 7.1 lakhs. So you can think of it as that you invested 7.1 lakh rupees into this enterprise. And compared to the ideal, so what would have been the ideal? You would have used directly the plan P3 at this location. So if you knew that the query was located at 5%, you would directly have used plan P3 because you know that's the ideal in this range of the selectivity space. And that would have cost you only the last one, which was the 3.4 lakhs. So the amount of overhead or investment that you're paying is 7.1 divided by 3.4, which is 2.1. And you can do some fairly obvious optimizations here, which I won't go into, which will bring this down to 1.8. But what you might say at this point is, look, this was a specific case that you showed, where you showed that you got a suboptimality of around 2, but maybe there are other locations here where it will behave much worse. But this slide that you see next, which shows you now that there was a green line, which was the ideal. This is essentially the oracle or the God's algorithm is green line. Red line is what you see here is what you would get with often with current database optimizers. And if you look at the plan bouquet, this is the blue line that you see in between. So the plan bouquet, even in the worst case, never exceeds 3.1. And the 3.1 comes now in the center here, not at the two extremes that you saw before, which was for the current optimizers, but in the center, it's at most 3.1. So you might think that, well, okay, you showed us that over the entire selectivity range, I'm never doing worse than 3.1. And notice that this is in comparison to the 100 that you had here, which was the maximum suboptimality for the native optimizer. But you might now say that, okay, this was for a specific query that you asked, which had the course.fees should be less than 1,000. Maybe there's some other query where you will actually do badly and you will do worse than the native optimizer for these database systems. And in fact, but what we can actually show is that this is not actually true, because if you look at the way that we are making these investments, essentially this is on the x-axis, what you have is the selectivities. On the y-axis, you have these costs. And essentially what we are doing is to follow a staircase. And how does the staircase go? The staircase goes as a geometric progression. So the total cost we are paying is in the normal sense of the geometric progression. You initially pay an initial investment of A, then you increase it to A plus AR, then you do A plus AR squared, where R is the common ratio, and so on, until you come to this final stage where you actually complete the query. Okay? So you have a staircase of investments which you are paying, and that can be expressed in this first line that you see here. So you pay the cost of the first, so the IC stands for the ISO cost cut, which was the 12,000, the 24,000, the 48,000, and so on. So this is the first cut cost, second cut cost, all the way up to here. This is last cut one, and then you finally did it with the plan P3, where you invested this 3.8 lakhs, and that was sufficient to complete the query. So the total cost incurred by the plan bouquet algorithm is the sum of this geometric progression. And that is shown by this expression here, which is the standard high school arithmetic that you have, which is A into R to the power of K minus 1, where K is the number of jumps that you had, divided by R minus 1. Now, in comparison, the cost that would have been paid by the ideal algorithm, which already knew where the query was located, would, in the ideal case, be located here. Because remember that it is possible for us to do a jump to the next plan. And if the actual selectivity was located just to the right of this particular cost or the ISO cost cut, then it's possible that you may be paying an unnecessary cost because of having jumped to the next level, which would be twice the original cost. So the best that could have been done by any ideal algorithm would be this, okay, which is one step below in this geometric progression. That would be A into R raised to the power of K minus 2. So now if you take the ratio of these two, you can show that it is expressed like the what you see here in this expression here, or this ratio, and this can be easily upper bounded to be R squared over R minus 1. So notice that there is no dependency on K here. So irrespective of where the query is located in the selectivity axis, you can bound the suboptimality to be R squared over R minus 1. And then with a very trivial optimization, you can show that this recess is minima at R equal to 2. So when R is equal to 2, this suboptimality becomes 4. So at this point, you might say that, oh, maybe there is an alternative algorithm compared to Plan Bouquet, where you can get a better value than 4, where the maximum suboptimality is, let's say, 3 and not 4. But actually, I would advise you not to do that, because we have been able to theoretically also show that this is the best possible performance that is achievable by any deterministic online algorithm. That is, it is not possible to design an algorithm that gives you a value better than 4. So the Plan Bouquet is ideal in that sense. And this is within the deterministic class of algorithms. So many of you would also have seen randomized algorithms. With randomized algorithms, you can do better. And if you look at our papers, you will see that we have done a detailed analysis also of what you can do with the randomized world. But in the deterministic world, this is the very best that you can do, is to get a value of 4. So one way of interpreting 4 is that this is 25, so you can get a performance that is 25% of the ideal. Okay? So the ideal is an MSO of 1. Your suboptimality is 4, which means that you are 25% of the ideal. Now, by itself, this may not look very good, saying, oh, I'm only 25% of the ideal. But remember that often the MSO values would be in the hundreds, the thousands, and the millions in the real world practice. So what we have done is to take an absolutely terrible solution and made it only mildly horrible. Okay, so now does this actually work in practice? Here is the performance on the Postgres SQL engine. So on the x-axis, these are various queries that you can see which come from the well-known database benchmarks. So I don't have the time to go into detail on that, but just assume that each point here on the x-axis is a fairly complex, well-known query in the real world. These are not just one-dimensional queries. The initial prefix that you see here, like 3D, 4D, 5D, and so on, refer to the number of different dimensions in the selectivity space. Okay? So earlier we had shown you a 3-dimensional cube. These go even higher than that. They go to 4 and 5 dimensions. On the y-axis, you see the worst case degradation behavior, which is quantified by this MSO, which is maximum suboptimality. And again, this is on a logarithmic axis. So it goes from 1, which is the ideal you can have, all the way to more than 1 million. So this is 1 million here, and this is 100 million. Now the red bar charts that you see, these correspond to the native Postgres optimizer. And what you see here is that it is often possible for the Postgres system, in hindsight, to have produced a plan which had actually very poor performance compared to the ideal. Okay? The height here that you see here is the amount of degradation. And notice that you even have queries like the one that you see here, which is with a benchmark query from the TPC-DS benchmark, where Postgres is doing more than 1 million times slower than the ideal. So as I said in the beginning, we are not talking about 20% degradation, 30%, and so on. These are in orders of magnitude. So in this particular case, Postgres have been slower than the ideal by a factor of 1 million or so. And then you see many such skyscrapers here with regard to the Postgres performance. Now, if you look at the Plan Bouquet algorithm in comparison, that's the green lines that you see at the bottom. And you can see that they're all within a factor of around let's say around 30 to 40. Okay? Now 30 to 40 by itself is not great, but as I said, compared to the skyscrapers that you had with Postgres, this brings the problem down to a much smaller number. Now this was done with the Postgres public domain system. This was also achieved on a commercial system, which I can't show you for legal reasons, but if you look in the paper, we do refer to that. And this was also proved to be the case that the commercial system had orders of magnitude degradation performance, whereas in comparison, the Plan Bouquet approach can complete within a factor of, let's say, 20 to 30 times of the optimal. So in summary, using this Plan Bouquet approach, now for the first time, we are able to give guarantees, and we give bounded performance suboptimality for the first time. This was not achievable before in any of the database engines. As I said, you always had to cross your fingers and your toes, and you had to pray very hard in order to get a good plan. But now you can be assured of a certain basic quality of performance. Something which may not have been obvious to you, but if you read the paper, it gets explained well, is that it's also robust to changes in the data distribution. So it's not a function of the database that you have below you that these guarantees are dependent on the contents. It's independent of the data distribution. It's this approach of Plan Bouquets is also easy to deploy. You can do this as a layer on top of the existing database engine. The reason this is very important is normally database engines are not tinkered with because they're extremely complex pieces of code. They're very large in size, and it's very hard to make any changes in them because of the potential side effects. So software engineers would typically suggest to you not to go and make any of such changes. And therefore, it is one of the advantages of the plan bouquet approach is without doing any invasive changes to the internals of database engine, you can deploy this on the top. If you're willing to allow to making some of the changes within the database engine, then we can give you even better guarantees than what I showed you here. But in the worst case, if you don't want to have any changes to the existing system, we can deploy this as a layer that is completely above the database engine. And finally, something which is very important in industry is that you want the repeatability in execution strategy. That is, you don't want because of certain changes that you made, that a plan that was being used before now changes to something else, and now the performance is completely different. That is achieved by the plan bouquet approach, because always we never do an estimation, as I mentioned repeatedly. We assume that the initial selectivity is 0 and that the subsequent behavior depends only on the actual location, which is dependent on the database contents and is not dependent on the execution strategy. So it's independent of the metadata. So we have been working on this for the last decade or so. So there's a lot of information that you can get off our website on this particular topic. So there is the initial concepts paper, which came in the SIGMOD 2014 conference. Then there was a subsequent demonstration of the software which implements all these ideas in the VLDB 2014, where it also got the best demonstration award in the world. Then there was a subsequent ACM transactions on database systems paper in 2016. So there was some follow-up work in the ICD conference from IEEE, where it also got the best student paper award. Then in the IEEE transactions, knowledge and data engineering, we had a full-scale version of this follow-up work. And then last year, I gave a tutorial on robust query processing, in which highlighted this plan bouquet approach as well, along with many other works in the robust query processing arena in the ICD conference of 2019. So the takeaway here is that if you have the SQL query and would like optimal query execution performance, unfortunately, in the native database systems, you had this dragon which would come and ask you this very difficult question saying, do you know the correct selectivities? And it was very difficult to negotiate this dragon. But now we have been able to do a Gandhigiri approach where you are able to offer some flowers in the form of plan bouquets to this demon or dragon. And thanks to that, now we can actually guarantee you near optimal performance. Okay? So with that, I'll end this presentation. And I think I saw that there were several questions on the chat channel. So let me just move on to that. You see this here. Okay, there were some questions here. Let me just go.
Yeah.
Yeah. Okay. So there was a few questions here. There was one from Asrar Ahmad. Okay. So the question is that let me repeat this for you in some for those who are not able to see the chat channel. The Asrar Ahmad's question was that, are the plans in a plan bouquet independent of each other, or are there dependencies? And is it that the particular sequence determines the optimality? No, there is actually no dependency here. Each of the plans is ideal in its own location. So as I said earlier, you may find that for certain kinds of pitches, you might find that Lakshman is the ideal batsman. For other kinds of pitches, Rahul Dravid is the best. Somewhere else, Virat Kohli is the best, and so on. So what we are saying is that we don't know the wicket in advance. What we will do is that we will assume that the wicket is flat and bring in, let's say, Virendra Sehwag initially. If that turns out to be a bad idea, then we will move on to Rahul Dravid. If that turns out to be a bad idea, we will move on to Virat Kohli and so on. So all these are independent players. And then based on how the wicket is turning out to be, I will go through this sequence of plans. So I'll start with assuming it's flat and progressively go on to harder and harder cases. And maybe if it's a very bouncy or a wicket, or if it's a spinner's paradise, eventually I'll wind up with VVS Lakshman, who is the best able to handle these kinds of difficult scenarios. So I progressively go through it, and the optimality is independent of this choice of plans. And then Professor Sudha Pelluri has a question that, is there any related work in the world of NoSQL databases. This is a very relevant and extremely good, well taken question. So one of the things that I did is that I only talked to you about relational database systems through this entire talk. And that was because in the entire enterprise world, essentially relational databases reign supreme. But over the course of the last decade, as she has correctly pointed out, you have had this notion of NoSQL coming in, which has a very different flavor to the SQL world that I presented in this particular talk. And many of you might have used these various kinds of systems, which are usually built on a Hadoop platform along with MapReduce, and the various kinds of databases like Hive and so on. The difference is that the NoSQL world is meant for scalability, whereas the enterprise relational world is meant for giving you these asset semantics and transactional semantics, which are often not available in the NoSQL world. But in the NoSQL world, over time, what we have found is that now people have kept finding that many of the properties that were there in the transactional world are required even in the NoSQL world. So nowadays, people actually don't call it as NoSQL, they call it as new SQL. Okay? So because they are bringing in many of the features that were there in the transactional world back into the NoSQL world. So for example, this notion of integrity constraints, which was initially not there in NoSQL, has now come back into the new SQL world. But modulo that, one of the things that you will find is that in the relational world, it's possible to build these optimal query optimizers because they have a mathematical foundation. And therefore, you can actually prove that given the correct inputs, the output plan that is being produced by the relational query optimizer is actually the ideal plan. In the NoSQL world, there is no such equivalent mathematical foundation. Okay? They're all built on essentially heuristics. And once you're built on heuristics, there are no guarantees that one can provide. So even with the ideal inputs, there is no guarantee that the NoSQL world will have the ideal plan because it lacks this mathematical foundation. Therefore, these ideas will not directly translate to the NoSQL world unless those tools have a mathematical foundation. If they had a foundation, then you can certainly use the similar kinds of ideas. So the ideas will still work, but the ideas will work as long as there is an underlying implementation that has this strong foundation on which optimality can be proved. So in the new SQL world, some of these ideas are now being implemented with proper database query optimizers, which have, as I said, these kinds of foundations that are built into it. On them, you can actually come up with the same idea of plan bouquets can be used even in those contexts. Yeah. Okay, and then there are some questions which can probably handle by the ACM chapter about e-certificates and so on. Are there any other technical questions? Okay.
Are there any questions from the participants? So now may I request Harista to give vote of thanks.
Thank you, Kavita. It's been a wonderful lecture by you, Professor Jayanth, and thank you so much for supporting the Hyderabad Tech-In chapter. And we look forward for inviting you personally and have interactions with you. Database has been in and around, when the computers are in and operating systems were developed. It's a very old software, but still you have brought out very new things that could have be possible, and current research that is going on. In fact, we can look at the optimization part, and the plan part was excellently discussed. And the future, we can think of multi-objective optimization, evolutionary algorithms, and other things coming into databases. It may be the future. We can look forward to this. And thank you so much for taking out your time. And see you soon. Thank you. Thank you all.
Yeah, so it was actually my pleasure to be here at the inauguration, and I again wish the new ACM chapter in Hyderabad the very best, and look forward to very novel and exciting ideas coming from all your students and the faculty there. I also just wanted to mention that I noticed that there were a few comments on the chat session asking for the slides. So what I'll do is that I will email a link to the tutorial that I gave last year in the ICDA conference. That was actually a 3.5-hour tutorial. So as you can see, it's a fairly broad field with about 200 slides or so. I'll email the link to Professor Naresh and Professor Sudha, and they can forward it to the other ACM members. And you can pick up the slides from there and then work your way through it. If you had any questions, you're free to and welcome to email them to me, and we're happy to respond to them. And again, thanks for your patient listening.
So that's a great help. Forwarding the link would be great help. Thank you.
Thank you, sir.
Okay, goodbye.
Goodbye. Thank you so much.
Good day, sir.